Hey Scholarship kids, and welcome back to lesson 5, part C. So this is the final part of this lesson. Today we're going to cover the 2006 exam question 6. So this question, it's saying vitamin C, which is this structure here, can be oxidized by bromine or iodine, doesn't matter which one. Okay, shown by the reaction below. So it forms this and you form 2Br minus, okay? This reaction is used in a variety of different methods for the quantitative determination of vitamin C in fruit juices. The bromine or iodine used in the titration, which is talking about up here, is generated by adding excess amounts of KBr or Ki to an acidified solution of bromate or iodate. Bromate is BrO3 minus and iodate is IO3 minus. You'll get very used to these because these are the VIT-C reagents we use. So essentially what they're saying is we add bromate to KBr or Ki, doesn't matter if you're doing the iodate one, and it produces bromine, and that bromine then reacts with your VIT-C up here to do the titration, okay? And then so there are two methods that they're going to discuss. So here's method 1, and we're going to answer method 1 and then we're going to answer method 2, because method 1 is all about theory stuff and it's stuff that you would never know unless you'd seen this stuff before, and so it's quite a good time to kind of introduce it. Some of these points are those points that I would get you to write in the back of your book as points that, you know, you just kind of have to know or get used to knowing. So it says here, an excess of standard potassium iodate, okay, IO3 minus, is added to the fruit juice sample along with potassium iodide, which is Ki. So we just saw in the reaction before, I minus and IO3 minus react to form I2, which then reacts with the fruit juice, okay? So reacts with the VIT-C. The amount of iodine that's produced from this reaction would be in excess. So that means that your I2 produced would react with the fruit juice. So no more of the fruit juice can react, okay, so that's all gone. And then the excess I2 is then titrated with thiosulfate, good old thiosulfate, which we know really well in a starch indicator. Okay, so I've just outlined that here, just so you know. So it then says iodine is only slightly soluble in water and is volatile. Volatile means it easily turns into a gas at room temperature. Iodide is oxidized by atmospheric oxygen. This point here is probably the most important at giving you the hints as to what they're getting at in this question. So the first question says, this part of the question is, explain how the accuracy of the experimental value for VIT-C concentration would be affected by 1. Vigorous swirling of the solution during the titration, 2. Allowing the solutions to stand before being titrated, and 3. The fact that excess iron in the solution can react with iodine to produce I3 minus. So they're asking you to discuss these 3 points. Would you know them if you'd never been taught them? Not likely, and so we're just going to talk about these now, and then method 2 is a calculation. Okay, so the first one that we're going to talk about is the vigorous swirling of the solution. Now, when you put the KiO3 with the excess Ki to produce I2, the I2 is not very soluble, and we actually do this titration in scholarship one time. We'll probably end up doing it in the term 3 holidays. So when you swirl, you will increase the amount that dissolves, okay, which is a good thing because you don't want the solid iodine. However, and the only way you would know this is from reading those points, the I minus that is produced in the reaction with thiosulfate, which is the final step of the back titration, can react with oxygen in the atmosphere and be oxidized to I2, and that's problematic because remember that final stage is I2 reacting with S2O3 2 minus. So if you end up producing more I2 from swirling than you actually should have, because the I minus that is produced is then reforming I2, then your value will be completely wrong. So the only way that you would know that answer is by reading that question and being able to interpret it, and I doubt many kids were that year, but now you've seen it, okay? So let me know if that doesn't make sense. The next part is it says allowing the solutions to stand before being titrated. it's never a good time to leave titrations for long periods. And in particular, it did say that I2 is volatile. And if I2 is volatile, it means that it's going to, you're going to lose some of your I2 before it can be accounted for in the titration, which is going to make your value for Vit-C incorrect. The third was excess iodide can actually react with iodine to produce I3. So in that first step, we add excess I minus, and so you actually end up with I minus always being in the reaction vessel, and so and it can react to form I3, which is problematic. So you can see here in the first stage we've got excess I minus, and all of the iodate reacts, and so there's excess left over, and then we produce some in the final step. So unfortunately, it can increase the amount of I2, so which can increase the amount of thiosulfate, and then the Vit-C ends up less than actual. And so therefore, that can be problematic, or it could cause a decrease in I2, which causes a decrease in this, and then Vit-C is more than actual. So this can actually be problematic, depending on which way of these reactions you talk about. So hopefully that makes sense there, is the fact that this can actually be quite problematic, because if you end up using some of your I2, then that means less of this is actually going to react, which results in less number of moles of this, and therefore your corresponding Vit-C will actually look like it's more, because it'll look like you ended up having more, or otherwise it's the opposite could happen. Okay, hopefully that has made sense. So let's go on to the really part that I really want to focus on today, which is the calculation aspect of this. So a standard potassium bromate solution was prepared by making 1.3 grams of potassium bromate in a 500 ml volumetric flask. And then it's diluted by taking 100 mils and putting that into a 500 ml volumetric flask. It says that 50 mils of fruit juice was mixed with 5 grams of KBr, which is excess KBr, and 20 mils of sulfuric acid. The sulfuric acid is just there to acidify, so we don't have to worry about that. The resulting mixture was titrated against the sodium bromate until you see a faint yellow colour, which indicates the presence of bromine. And at this point, 14.04 potassium bromate had been added. Then 3 grams of potassium iodide and a starch indicator were added, and the iodine produced required 2.36 mils of sodium thiosulfate to reach the endpoint. Calculate the percentage of Vit-C in milligrams and comment on the validity of the results. So what we're going to start with is actually what's happening, because it's a bit more complicated, this titration. So what's initially happening is you had the bromate solution, and we added the KBr, and that's forming the bromine. And then we add the fruit juice, and the fruit juice is going to react with that bromine, and there'll be excess bromine, okay? So the point when the color change happens, because we add the bromate, if you actually look back at this question, it says that you actually titrate with the bromate as opposed to just plonking it all into the flask. So that's a little bit different to what we've seen. So you keep adding the bromate, and when you start to see an orangey yellow color, that tells us that the Vit-C has fully reacted, because now we're just seeing excess bromine being produced. Okay, so what then happens is they then add Ki. Okay, and why are they adding Ki? Because the excess bromine that was left over, the iodide will react with that to produce I2 and Br2, and then the I2 will then react with our lovely thiosulfate with the starch indicator, which we all know. So this is the sequence of steps. I'm going to say it again to make sure we've got it. So basically, if we go back, just to make sure everyone's got it, they had made a standard bromate. They took 50 mils of fruit juice and added the KBr, and then they titrated with the bromate. Okay, so Vit-C is in a flask. Okay, and what they do is they add excess KBr to this flask. So that's fine, nothing will really happen. But when bromate starts being added, the bromate reacts with the bromide and produces bromine, and that bromine is going to react with the Vit C. And when all the Vit C has completely been used up and has been changed, you'll be left with bromine. And we know that because we start to see this orangey yellow color, which is indicative of bromine. So once we've got the bromine, that's the signal to then add excess Ki, and we add excess because we're trying to ensure all the bromine reacts. So the bromine forms bromide, and the iodide forms iodine, and then the iodine reacts with our trusty thiosulfate in a final titration. Okay, so we can see here that 1 bromate produces 3 bromine, and so if that's 3 bromine, okay, then that's going to produce 3 of these I2s, because that's a 1-to-1 for that part. And then if you've got 3 I2s, it's going to produce 6 thiosulfates. So if we're trying to compare bromate to thiosulfate, it's actually 1 bromate to 6 thiosulfates, and that makes our calculation way easier. The FAF in the middle you can actually ignore, but there's multiple ways you can do this, and I'll show an alternative method for those who like it. I just do the easiest one. So always just go through like that. So they gave us the mass of bromate that they added. So mass divided by molar mass, that gives you the number of moles. And then we can work out the concentration by doing N divided by V. It was 500 mils, okay? Now, be mindful that it was then diluted 100 mils into 500 mils, so by a factor of 5. So I'm going to divide that concentration by 5, and that's my diluted concentration of bromate that was used in the question. A lot of kids forgot that step in the exam, and so they lost marks. So then, so what we can do now is we can work out how much bromate was added, and so the bromate, and that's an excess, remember, so they added more bromate, and so therefore there was extra bromine produced. So that gives us the number of moles using that concentration there. So N, and that was the volume given. And so if we've got the number of bromate, what I'm going to do now is work out the thiosulfate from the values given. So we can work out the number of moles of thiosulfate that reacted with the iodine, and that's that number of moles. Now we know there's 1 bromate to every 6 thiosulfates, which we just did before. And so we can work out from this thiosulfate value, we can work out the number of moles of bromate that had reacted in excess, or how much bromate had been left over after reacting with Vit C. And so 1/6, we're trying to find the number of moles of bromate, so we times it by 1/6. So we take our number of moles of thiosulfate from that final step, times it by 1/6, and this is the number of moles of bromate that reacted to form Br2, which then reacted with Vit C. Okay, sorry, that didn't react with Vit C, because this is the part that reacted with your sodium thiosulfate, S2O3 2-. Sorry, hopefully you didn't get that confused. I'll say that again actually just to make sure. So what we've just calculated here is how much bromate reacted with the thiosulfate. Okay, so it's the excess amount. So now we can work out the amount of bromate that was used to react with the Vit C. Okay, and how we can do that is we can do, here's the total amount of bromate that was added. So if we've got the number of moles that reacted with the thiosulfate, then we can subtract them, and that's the number of moles of bromate that reacted with the Vit C. Okay, and from there, what we can do is look at this equation, and it's a 1-to-1 equation. So every 1 bromate reacted with every 1 bromine reacted with 1 Vit C, and 1 bromate produced 3 bromine. So this is a 1-to-3, okay? So therefore the number of moles of Vit C is going to be 3 times the number of moles of that bromate that we just got, and that gives us that number of moles. And then we can finally turn that into a mass by timesing by the molar mass, and you end up with 0.023 grams or 23.1 milligrams. So I hope that makes sense. Let me know if it doesn't. And that's the end of this part of the video.